right. You guys can start checking the evens. Number 6. Limit is 0, so I forget who you were comparing. Square root of x is faster, right? Who were you comparing for number 6? ln of x is slower. Square root of x is faster. I don't know which way you said it, but you could have said it either way, right? Yeah. ln of x is slower or square root of x is faster. Number 14, the final limit is e, which means they are the same. They are growing at the same rate. Remember, whenever the limit is a constant. Ooh, how many of you guys actually got that the limit was e? Anybody say it was 1? Ah, you said ratio of the leading coefficients, 1 over 1. The problem is you forgot the plus 1 exponent properties. Isn't that the limit as x goes to infinity of e to the x times e? Woo! What's the ratio of the leading coefficients? E over 1. Ooh, you just saw 1 over 1 and you said done. Ah! Exponent properties. If you see plus 1, it's times that base. It was tricky. It was tricky. I give you that. I give you that. I caught you on one, though. Okay, number 18. Number 18. E to the x is just reduced. My limit is infinity, so isn't the top guy growing faster? Right? Or the bottom guy growing slower? They give that to you in the statement. Number 26. David, this kind of answers our question because they're actually stating in their answer as x goes to infinity. So that's why we were doing it, is because they were only asking for that direction. So not x going to negative infinity. He was asking that yesterday, like, do you compare going to negative infinity? Because if so, then e to the negative infinity is very different than e to the positive infinity. But they're only asking us to go to positive. Number 2, square root of x grows quicker because the limit is either infinity when he's on top or it should be 0 if he's on bottom. It depends on which way you placed him as to whether you should be getting infinity or 0. Just be careful. If you wrote it the other way, no big deal. Your limit should have just been 0 and it would have shown the exact same thing, which is nice. Number 32, comparing the two functions. You can see them putting the square root of x to the 4th plus x over x squared, which most of you would have at least seen it was a tie, whether or not you exactly knew, but the square root of a 4th degree is a squared, right? So technically tie, whatever the limit is, you don't even need to know it's a tie, so therefore you can say same rate. You can keep comparing same rate, and by transitivity, just by doing 2 comparisons, same, same, therefore the outer same is this one same, okay, they're all the same. You could have compared 3 different comparisons, but 2 were sufficient. Number 48 is E. Number 50 is C. Oh, you guys didn't check your or catch your mistake on this one when the answer was E squared? Or did you put it as 2? Or 1? Was 1 an option? It would have been so sneaky if 1 was an option. What do you guys not know? What did you put as your answer for 50? Did everybody get C? Oh, so you figured it out there. Okay. Because this one is E to the x times E squared. So that one is very similar to the other one. You're just going too fast on the other one. Oh, how did they do this? Why are there factorials? Most of you just said top wins and infinitive. How did they do 6 factorial over 5 factorial? Why is x to the power of 1 when it was x to the power of 6? And why is the bottom x?
Maybe it's some property.
What property? Where did it come from?
L'Hopital.
How many L'Hopitals? 5. 1 would be 4th, 3rd, 2nd, 1st. Good. Gone. 5 L'Hopitals. What happens when you do 5 L'Hopitals? Doesn't the 5 come down? Then doesn't the 4 come down? And doesn't the 3 come down? Then doesn't the 2 come down? And doesn't the 1 come down? And in that process, didn't 6 and 5 and 4 and 3 and 2 and 1 come down as well? Well, actually, the 1 wouldn't have come down, but you would have a 2 times 1. 6 factorial over 5 factorial. What would happen if you had done L'Hopital's rule over 5 times? Who wins? The top does. Infinity. They did L'Hopital's in a repeated fashion without showing it 6 times. They didn't just say top anyone. Only works with polynomials, but snazzy. Wait a minute. Wasn't there an x to the, was it 1,000? 100?
Oh.
Couldn't you have done the same thing on that and not actually taken, but still shown what would eventually end up happening? Couldn't you have had 1,000 factorial? As the constant on the bottom, the x would be gone at that point, and on the top, I think you had like an e to the x who would have stayed the whole time. What number was that? Do you guys have it? Oh, it was an odd. Here he is. And you were comparing him to just e to the x? Oh, that's not even as fun. If it was like 2 e to the x, that'd be more fun. So you'd have 2 to the power of 1,000 e to the x. All right, fine. It would have just been e to the x over 1,000 factorial. Top wins, infinity, and I showed you what 1,000 multi-pals would have done. Oh, coming back. Oh, wrong one. Wrong one. Sorry. Coming back. Are we done? Oh, yeah, we are. Okay, you guys have odds or evens that you got stuck on. Anything we need to talk about? 51. 51? Is that the x to the x element of everything? Oh, it's not. We figured that one out. Okay. P.S. What is infinity to the infinity power?
Infinity.
Infinity. What's infinity over 0? Infinity. Because isn't any number over 0 infinity? And so thus, if it was infinity over 0, it would still be infinity? Wait a minute, but if you have 0 over infinity, isn't that indeterminate?
0.
It's 0 and 0. Well, I'm just saying stuff, and it doesn't make sense to you. It just makes sense to me. Anyway, there are some forms that we don't see a lot that showed up in this homework that some of you were like, but that's indeterminate. It's not. You had to grapple with that just a little bit, especially in whatever number that was. They're saying what your following functions goes. Same rate. Ooh, same rate is a function such that if I set the ratio of this guy to that guy, it would equal a constant, right? Well, this will only equal a constant, a ratio of the leading coefficients, or a 0, if the bottom is stronger, because that would be 0, or if the bottom is tied. But what's the degree of this polynomial right now? Degree is 4. So I need something that same rate. Oh no, if it's 0, the stronger one, that doesn't work because the stronger one, 0, that means the bottom is faster. That doesn't work. Those ones are going to be too small. The top is stronger, so then he'll be faster. Only this one will their degrees be tied, and that will be a ratio. Does that make sense?
How do you know that polynomial degrees?
Because I am thinking, okay, here's to be honest, I'm thinking in my head, what if he wasn't there because he's not as strong as him? I'm only looking at the champion or at the highest. Because the end behavior model of this, eventually, for sufficiently large values of x, being all snazzy, this will look like an 8th degree polynomial, right? But it's square rooted. So I'm thinking of x to the 8th square rooted, which is, x to the 8 over 2. Remember how exponents work? Or you can think x to the 4th times x to the 4th. Either way, it's a 4th degree polynomial. But mathematically, we could also be thinking of the old-fashioned way of solving this limit would be using algebra, which would be multiplying by 1 over x to the 4th and 1 over the square root of x to the 8th. That's technically an absolute value. Then I would bring this in, which would be the square root of 1 plus 1 over x to the 4th. Only would an x to the 4th I could just make that one. No, because always positive, always positive. Okay, I'm good. Only x to the 4th would have all variables gone with just this guy going to 0. Anything else, there would have been either a remainder down here or a remainder up there. That would have made the limit either 0 or infinity. Okay. Anything else besides number 51? Oh, wasn't as bad as I thought. Not that it wasn't hard, just that we made it. Okay. Section 9.4. What's really nice is we just have to start it. Sound good? Which means this homework isn't due on Tuesday, but it does mean we're done with it on Wednesday, and it's the last section of chapter 9.
They tell me the test is next Friday.
Which means the test is when some of you are gone to Magic Mountain. Or it's on a Monday and we have a work day when you're gone to Magic Mountain. So I'm pondering life as to whether to have it on a Monday or whether to have it on a Friday, and so you have to make it up. I tried to cram it and like save a day and have it Thursday, but I couldn't. I don't know how. If we had school Monday, it would have been great. But nobody wants school on Monday, so Saturday. You don't want that. Because the kids that are, like, the ones who will be here at school wouldn't mind a work day on Friday. Like, I'm pretty sure they'd be fine with that. But then no one wants a test on Monday, so it's like, well, we have less time. But we could go into lunch, because you guys are 5th period. Like, we do that anyway. Senior Student Council would have a meeting on Tuesday. I don't know. We'll see. We'll see. We might have to vote. I know. Because I'll be missing 1, 2, 3, 4. Yeah, 4 of you. And Gavin, 5 of. So, I don't know. We'll do it. We'll do what we think is best. You guys don't need me to show you the calendar. The test is next Friday right now, unless I move it to Monday, which gives you a little bit of extra time as far as the review and as far as asking questions. It's just a bummer because who wants it on a Monday? But it would give extra time. And my kiddo's going to Magic Mountain next Friday. Wouldn't have to miss it, which would be nice. So that's kind of what I'm thinking, but I'm not sure it's completely decided in my head. But long story short, we still want to. Oh my goodness, I don't have your notes open. I am so sorry. We still want to start section 9.4 today either way, because it'd be nice if next Friday, if it is a work day, is like you guys reviewing, not like you guys barely getting to the review. It'd be nicer if we've covered everything, done questions on everything, and you guys are just having like a day and a half to review. And maybe throw in like a bonus AP classroom, which would be nice too, but I don't know, we'll see. We're getting it up, Section 9.4, title. You guys can fill that in. Improper integrals. Now, I've shown a few people improper integrals just because they were curious about that number 10 on Barron's. Or I think there was another one that kind of involved an improper integral as well. But the majority of us, we haven't really dealt with it a lot. Oh, these were extra, like, L'Hopital's. Okay. Here we go. I'm going to leave this one solved. I'm going to freeze the screen. I'm going to leave it solved. You guys can work through the example. I'm just curious if it can all make sense. I'm curious if all of this can make sense. So section 9.4, improper integrals. As you guys are looking at the example that I've already solved out down below, I'm going to go erase the rest of the examples. Man, these notes are just a mess. There we go. I'm going to go erase the rest of the examples. But I'll leave this one up because I think you guys should be able to track with what I'm doing. Or my question kind of is, can you track with what I'm doing? This problem shows the problem. There's an infinity in the bound going to infinity. Oh, well, that's silly. We never need to go to infinity in an integral because infinity, we're looking for finite areas with definite integrals. This is finite. No, but you're going to infinity. I know. It converges. It doesn't diverge. It stabilizes. It doesn't keep on expanding. Why does that start to make our heads hurt just a little bit? What am I saying? As this goes to infinity, which means more and more and more and more and more and more and more area. The area is not infinite. The area is just 1. Or negligibly close to 1. Shout out Mr. Hampton. Negligibly close to 1. For all practical purposes, 1. That's intense. He was like, does it, for all practical purposes, it basically hit 0? I'm like, yeah, for all practical purposes. And he's like, oh! I don't know, he said you guys were mad because you kept on saying that it would never hit 0. And in some ways, theoretically, it won't, but for all practical purposes, 0.0000 is 0. It's called Zeno's paradox. Remember? Go halfway, and then go halfway, and then go halfway, but my foot's not big enough to go halfway again. Oh well, I'm dead. Mathematically, forever, realistically. Hi, podium. Anyway. So, going to infinity. And yet the area is bounded. The area is not as far as its surface area, maybe? No? Because surface area is area. Interesting. An infinite region with a finite area. Minds start to get boggled. But guys, does my maths make sense? Why did I have to put a constant there? Why did I make that a b? Because infinity is not a number that I can plug in with FTC. Remember? We did quotes whenever we put infinities in. It's not a number. What is infinity? Ever increasing, sometimes slower, faster, sometimes lower, higher, but ever expanding. Right? So I can't put an infinity in as a number. I couldn't have an infinity there, but what can I legally, mathematically do? Ah, look, it's a variable. Hey, I can plug that in, and guess what's happening to the variable? It's approaching. So what happens? I anti-derived. I plugged in b. I plugged in a. I took a limit, and guys, what's the limit of negative 1 over 0? What's 0 plus 1? You just found an infinite areas answer. Or at least a region with an infinite boundaries area. Whew, that's exciting. Yeah.
Well, like, couldn't it work like illegally, kind of? Like, you could do FTC illegally and say.
Yes, but they don't want to show it illegally. Like, could you put an infinity there and say 1 over infinity is 0? Yes, but that wouldn't be proper. Does that make sense? And we'll see in just a second that the. Well, let's just keep going forward. Hold on, what do you guys see up here? How to evaluate improper integrals. We either have an infinite limit of integration, aka an infinity here or an infinity there, or both. Now wait, if it's infinity over infinity, isn't that just 0 because you have it? Because you have a over a? Yes. But couldn't I have negative infinity to positive infinity? If I have any infinities in either or both bounds, it's improper. Or if I have vertical asymptotes, or any kind type of discontinuity. And this doesn't say just in the bounds. It could be a vertical asymptote at a bound, or it could be some sort of discontinuity within the bounds. Either I have an infinity in the bounds, or I have discontinuities either inside a region or at the boundaries of a region. Okay. Either way, we have lots to deal with. Guys, this is an Endeavor card. I'm not sure it's necessarily the most important of Endeavor cards, meaning once you practice it, I'm pretty sure it'll just be like common knowledge to you. It'll just be so natural for you to go ahead and use or be able to use. We're just giving you a heads up that it is a thing. Meaning, if I'm going to positive infinity, it should be the top bound because the top bound is the higher, and positive infinity on a number line is higher than anything else on the number line. I know, it's going to be noisy for a little bit. Hang in there. Okay, maybe I can't handle it. Let's just go a little ways. Okay, if I have an infinity as a top bound, let's just all call it b and have b go to infinity because we're used to the top being b. If we have a negative infinity on the bottom, let's just call him a so we can all have the exact same notation, and then a is going to go to negative infinity. No big deal. But if we have a negative infinity to a positive infinity, we have to split it up somehow because we can't take a limit to both positive and negative infinity at the exact same time. And we have seen before, especially with piecewise functions, square root functions, exponential functions, with horizontal asymptotes, that limits to infinities, different infinities can be different. They're not always the same. So we need to be able to take a limit of one and a limit of the other, going to one negative infinity first and then to positive infinity second. So we have to split it up. But here's what you guys need to realize. You can split it up at any x equals c. You might be like, well, any x equals c except for discontinuities. But hold on, wait a minute. Discontinuities, they should have been separated, split up as well. So technically, split up at any x equals c and discontinuities should have already been used. Well, that would just cause a whole other issue if you had a discontinuity and an infinity. You have to split that one up twice as well. So we want at any x equals c that is not a discontinuity, where the function is continuous. The integrand is continuous. Ah, that AP question. Number 10, where the integrand, where f is continuous. So at any x equals c, where little f. If the limit exists and is a constant, then we can say that the definite integral converges to whatever the answer is. And then if, now, we're not saying the area equals, we're saying the area converges to, gets negligibly close to, is basically bounded by, can be encompassed by, okay? But then if the limit either does not exist or is in, well, remember, an infinite limit technically does not exist, then we can say it's divergent, it meaning the integral, meaning the area. Are we on 11? I feel like we lost count somewhere, and I'm just making sure we're good. 12? Okay. This was last year's number, so I was just making sure. Not many of you are just like throwing it in your cards as we speak. Some of you are like, cards? What cards? Am I building any cards? Anyway. Don't know. Endeavor quizzes are coming soon. You will want those cards up to date just to try to get bonus. Okay. So with this, now, guys, this entire Endeavor card is just if we have infinite limits, right? Not really talking about discontinuities. Not really talking about the Berkeley question that messed up Matt. Although she should have known. And she did know. She's not kicking herself over. How would I integrate? Wait, what did we integrate a second ago? The example you wrote down, I already solved. It was the integral from 1 to infinity of dx. Okay, so dx over x squared, which is 1 over x squared dx. Oh, this one's 1 over x. It must be the same. Okay, let's go ahead and solve it. Wait, we have to rewrite it first. So it's 1 to b. The limit s, b goes to infinity of 1 over x dx. Okay, equals. Solve the definite integral first. Nope, you're deriving ln of absolute value of x from 1 to b, limit s, b goes to infinity. True? So now what? He was making a face at you because you won most wonderful international. Congratulations. Yeah, that's fun. It's probably close. Coming back. You guys are all memorable, though. Those most ones are always. Come back, come back. Don't we have solve ln of b minus ln of 1? Wait, isn't ln of 1 just 0? Isn't b going to positive infinity, so he's positive anyway? I mean, okay, whatever. But either way, guys, hold on. I know it's slow. I know it's slow going, but what does ln do as b goes to infinity? So the integral from 1 to infinity of 1 over x squared is 1, but the integral from 1 to infinity of 1 over x is infinite? That's weird. I told you. Some things in the next couple chapters, your brain is going to not understand because from what it knows, it doesn't make sense. But mathematically, I'll prove it to you.
It makes sense.
It does? Because it's a little bit more area? It makes sense because of the ln, but as far as like, wait a minute, this one and this one, he equals 1 and he equals infinity? It's weird. You have to at least admit it's weird. How does it make sense, though?
Because like 100 squared is like more wide. Showing the word deeper. Like,
You can say.
yeah, like more closer to the axis. Whereas like the 1/x have more area.
So more area makes sense, but infinite?
It
Or less area makes sense, but one?
It's just
Plain devil's advocate. You know that phrase in English? Devil's advocate. It means like, okay, if God is right and the devil's wrong, thinking religiously, in theory, if God is right and devil's wrong, playing devil's advocate is like, but what about this? That's what devil's advocate is. Okay, I'm trying to play the other side and be like, but isn't that weird? Isn't that strange? Even though it's true. Okay, what's on this page? Maybe it's from The Devil and Daniel Webster? I wonder if it's from that one. Or is that a story? It might be from that. The one where he like signed his blood in order for the devil to give him everything he wanted. Oh, he's gonna make that one. That's an interesting one. Screw tape letters where the demons and they're all talking about how to get Christians and how to make them basically ineffective. Because they're like, if we can make them ineffective, who cares about them? They're not doing anything anyway. Definition of improper integrals with finite, okay, here's the discontinuities. We were just talking about what if there's an infinity? No big deal. Make a variable and have the variable go to infinity. Solve it like normal and then limit. So what if there are discontinuities? Okay, I'm not making a forever card out of this because it's kind of weird and it's really similar. It's really similar to the last one with the infinities. What's different is instead of making like that, where are we at? Oh, that top bound, which we won't be able to plug in. It's a discontinuity, so it would just equal DNE. And those of you who are trying to do fuzzy math, okay, I get it. If you're really smart, you'll realize. But it's just going to be a number, and it's just going to get an over 0. So we're going to have to approach him also. So if the discontinuity is at B, we have to approach B. But B is the, wait, pause. Can I zoom in on these whole, like, from below, from above things and make sure they make sense? Is that okay? Okay, because they're saying from below and from above, but wait a minute, why are they saying all of that? Well, check it. Okay? If we were talking about a number line, A is lower, B is higher. Okay? If B is my upper bound, wouldn't I have to be approaching from below it if I'm talking about that region? So I'm assigning a letter C, so it's not the discontinuity, and I'm having that C go towards B from below. If I have a discontinuity for the next one at A, I need to come towards A from above, because the region outside of that doesn't matter. It's not being considered. It's completely irrelevant. And even technically at B and at A are irrelevant. What matters is what's in between going up to and what's in between going down to. So of course I have to do B from below and A from above, in case that doesn't make sense. And once again, down here, ooh, there we go. What if we have a discontinuity somewhere in between or multiple discontinuities? Well, then all of a sudden I have to split it up at C, and then I can do the exact same thing in the sense that now I have to have my D going towards C from below, this guy, from A to D. And then I have to have my limit as E, F goes to C from above, this guy. That's a mess. But if there is a discontinuity at C, I have to split it up at C just like I would have to do at an absolute value. I would have to split it up at that Now wait, I'm not going to see it. Ugh. I'm going to have to know it based on the, it was like the one number 10 in our AP where we had discontinuities of the function at plus or minus 1, but we were going from 5 to, that's weird, it was backwards. Oh, it was backwards. But anyway, if we have discontinuities in between, we have to split up the interval at those discontinuities and approach from the proper below, from the proper above direction. Let me zoom out because I know I lost some of you guys in scrolling. I'm sorry for that. Close the intention. Oh my goodness, you guys, we have such a popular class. We have most apps. We have most likely to brighten your day.
Right.
I like that word.
Cutest couple and best friends. We have cutest couple. We have most intelligent. We have Joe Tan, most intelligent. We have best friends. Oh my goodness, you guys. Go RBC class. There might be more. Who knows? They're just like coming in waves. Who wants to send Joe Tan a picture?
I will.
It says Joseph on here.
I'm like, which one?
That's hard. You guys had a hard class for these things. I didn't realize you voted. Oh no, I did.
A hard class. There's less people.
Somewhere. Bible class?
Bible class.
Yesterday? 2 days ago?
You were gone that day.
Oh. No campaigning. All right. Can we go ahead? Are we good? Which one? Oh. Here, I'll write it down here. If we're splitting up because it's a discontinuity, we can't keep C either. So we'd have to do that guy, the limit as there's a new guy going to C from below A to D. But we also couldn't have him, but we have to have another letter because it has to be another bound. So we'll do the limit as, I didn't use E because E is a number. I don't know, it's awkward. So we'll do F. No, I guess I shouldn't have used F either. Oh. Make it a G. Oh, make it a G. Because F is our function. Do you guys realize that we're going to be practicing definite integrals? But we're going to have variables in our antiderivative of top bound minus antiderivative of bottom bound. We're going to have B's and A's and D's and F's and other things that we're going to be taking limits of. So why does it make sense for improper integrals, something new we still had to learn, integration, that we did L'Hopital's and we did relative rates of growth right before it? What's the common thread? Limits, 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 right? Limits, limits, limits. What was 9.1? I actually don't remember. Oh, we were going to infinity because we're getting ready for the sequences, not series, and series that are coming. So we're starting limits, and then limits, and then limits, and then limits. Huh. I wonder if they should have gone first or last. Oh well. Should have. Who knows? It's just an opinion anyway. All right. Ready? Set. There's no infinity. I don't get it. What's the Right? 0 is a vertical asymptote. Oh, I can't just plug in 0. Yeah, you could. Anti-direct? No. It's a discontinuity of the original integrand. Whether or not you could later, you need to take a limit. Meaning, I need to go ahead and say, okay, limit as A goes to 0 from?
Top.
Good. From above, because it's this region that's above 0. Does that make sense? I can't come from this way. There's no purpose. That's not the bounds. I need to come from above. And there's my integral from A to 1 of x to the negative. Oh, hey, I can do this when I rewrite it. I can kill 2 birds, 1 stone. AKA do 2 things at once. Use 3 English phrases. Now what? Although that one literally makes sense. Anyway. Hopefully you didn't visualize that. Anyway, power rule, right? Plus 3 over 3 is 2/3, and then times the reciprocal, which is 3 halves, and then nobody wants to deal with that. Let's put that under a cubed root, right? Let's do 3 halves cubed root of x squared. Because nice. Limit as A goes to 0 from above, this guy evaluated from A to 1. Right? So then I have 3 halves. I'm just going to be lazy. Cubed root of 1 squared, which is, that's just 1 to any power, 1, minus cubed root of A squared, but I'm taking A to go to. Now some of you are going to be like, oh, I hated those whole above and below things. Pause. Try to plug in just good old 0. Don't don't stress about above or below. What happens if you plug in go to 0? 0. What's 1 minus 0? 1. 1. And what's 3 halves times? Double check. If I'm above 0, like 0.1, does it still exist? Yeah. Even if you were below, it would still exist. I'm good, no matter what. Nothing got, like, illegally used or processed. I'm good. The above and below thing, it's more of just keeping everything legal and having your notation in line and making sense for what you're doing. But just try to plug in whatever constant you have. Dun, 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 dun. What? So that keeps going up forever, adding more and more and more. Equals 3 halves. But some of you are like, okay, I get it. Like eventually you're adding like 0.1, 0.01, 0.001, 0.00. Okay, I get it. It's basically, I guess it'd be more like 0.9, 0.99, 0.99. And eventually there's no instruments that would actually measure any difference between what you have and what you are saying. There is something interesting that happens if you have an integral from 1 to infinity of 1 over x to the p. And we kind of saw it in the beginning example. And this is probably where we're going to end today. Where are we at? We'll just end here. There is kind of a shortcut you can do if you have 1 over x to the p. Eventually when we're dealing with series. Okay. We're going to call it parting C. P series.
T series?
P series. But it's going to be n to the p, not x to the p. It's going to look a little differently. But anyway, P series. Parting C. P series. Alternating series test. Ratio root test. Telescoping. Integral test. Nth term test. Geometric series. Limit and direct comparison test. Whew! Parting C. All the different ways that we can see whether or not a series converges. Why not sequence? Because sequence is easy. Take the limit as n goes to infinity. Done. Series, there are 9 of them, and even then. Whew! Alright guys, we're done with this. I'm going to go ahead and get ready for Potluck Club. Potluck Club people, if you're sticking around. If you can get forks out of theirs, if you can get napkins out of there, plates, I really hope someone brought them, because I told you we need it. Yes. Thank you, Jesus. You can start putting the food around. I'm getting something to heat up Lainey's rice. Lainey, get me your rice. Then I'll come back and check my arroz con pollo that I hope is done.
I can remove the rice. Pollo, right?
Yeah,
Is it big enough?
Well, because it's like chicken thighs that were just put in with the skin on. Like you can just, like it's not chunked up.
Yeah.
BC Kids, you're welcome for all the